The objective of tonight is really to talk about, are we capable as a culture, or let's say a society, to be no longer a consumerist society, which we've been since the 90s, and to pivot to the point where we are then, again, developing and producing our own technology, so high-tech manufacturing. The mission of the Obama Institute's Rod Alferness, who's the Dean of the College of Engineering, will present, but we should all be looking with a really intense microscope at this, I would say, a experiment. So what I will have Rod Alferness, who was the CTO of Bell Labs and has been the Dean of the College of Engineering for the last 4 years, and definitely the rocket propulsion behind one of these institutes, give his view of what President Obama has initiated. So, Rod?
It's a pleasure to be here this evening. And so what I'm going to do is just give a little bit of an introduction to this national network of manufacturing institutes. And maybe I can just provide a little my own perspective. So I spent many years at Bell Labs working in the area of optical communications. And towards the end of that career, I spent 3 years in the business unit, the optical networking business unit, as a chief technical officer. And it was right around the year 2000, and it was right around, so I was in that business unit as we were going through the boom of telecommunications and the bust. But I also experienced what many of you have seen as well, is that as technology got more and more complex, interestingly enough, we were doing more and more offshoring of the actual manufacturing. That has been particularly the case in the case of optical equipment, fiber optics equipment, et cetera, et cetera. And so this issue of investing in the intellectual capital through universities and what go on in research institutions in industry, and then ending up manufacturing outside of this country has had very severe consequences and impact. And I think what we're talking about tonight is at least one approach that the federal government is coming up with to try to address that. So President Obama actually at a meeting of the National Academy of Engineering first kind of articulated his concept of something in this space. How do we bring back, or at least substantially reduce the amount of manufacturing that's going offshore? And it really is about to be maker of things, not just consumer of things. And it's really about a concept that if we are fundamentally a service economy and we make nothing, at some point that does not compute. And we maybe saw a little of that when we said we were we had the best core competence in financial services, and we were going to export those financial services, and we saw a little bit about what happened when that happened. So it's really about making things that change the way people live. And so, in fact, it was the effect of that outsourcing was dramatic. So this is a chart of essentially the U.S. balance of trade for advanced technology. And it's looking at it as a function of year. This is how much do we export in terms of manufactured advanced technology goods, how much do we import? And then we were net positive all the way up until just after the year 2000. And since that time, there has been a steady trend that more and more we do no longer make the gadgets and the advanced technology. And it's not just gadgets. There's a lot of infrastructure, very high-cost infrastructure that's around advanced technology, and increasingly that is being manufactured outside of the country, and we're buying it and bringing it back in. In spite of the fact that if you look in a number of industries, certainly displays, photovoltaics, and chips, batteries, the basic inventions and much of the early development of those technologies happened in the US, And then when that technology got mature and had to be manufactured, we said, no, we can't do it here. Even though in many of these cases there's a lot of automation, et cetera, at some point there's some packaging, there's some work that needs to be done by hand, and fundamentally companies will decide to do what is the best financially. And if that means putting it all together offshore, that's what will happen, in spite of the fact that, again, the basic technology was developed here. And so one of the issues about trying to bridge that, you know, we do the discovery, we do the technology development, and then somehow we don't quite complete the whole value proposition of making the technology. Sometimes that's referred to this valley of death, right? If we look at a function of time here and we look at where the investment is in universities and the government, we invest in research, we discover, we may even prototype. These levels here are manufacturing readiness levels. It says really how far along in that going from discovery to demonstrating a proof of principle. And there's always this kind of gap where we kind of have the technology almost ready, but can we invest that extra money to turn this into a real product or not? So that, and how far do we have to be so that the private sector sees, aha, there's a business here, I'm willing to invest. And so that gap is also part of this issue about making sure that we don't have to outsource all of our manufacturing. So that germ of the idea was expressed by President Obama in 2009. In 2012, he declared not just a vision, but a plan for how to execute on that, at least one model. And that model is a model of a national network of manufacturing institutes with the intent that ultimately there would be something like 15 of them, with the concept of helping to develop the ecosystem around advancing technologies, including elements of packaging and manufacture, and including automation in those, that would ultimately make sure or try to ensure that those technologies, those new products, could be evolved in a way that, having invented the technology, developing the technology, we would also have an ecosystem of companies that were providing the capability to manufacture that technology and those products in a way that was cost-effective in the US. So fundamentally, that's what these institutes are about, and there's a network of them kind of across the country with the intent that ultimately there will be roughly 15 of them. And so here is kind of where, how that's evolved. President Obama actually made the announcement about the approach when he also launched the America Makes. So that was the first of the institutes. It's a 3D manufacturing technology. The second one, Power America, is basically about next generation power electronics manufacturing, basically power electronics for the grid. Right? We all know that the electrical grid is aging, and with photovoltaics and other technologies, the nature of it will be changing. So it's really how do we build that infrastructure and the power industry and the power electronics that drives it in a way that we can actually do that manufacturing in the U.S. in a cost-effective way. That institute, UCSB is participating in. Umesh Mishra is the key person driving the gallium nitride solution for highly efficient power electronics, and you'll hear from Umesh in just a few moments. Number of other ones, digital manufacturing design, light wave innovations for tomorrow. This is in the Detroit area and is looking at materials for the automotive industry, and one in advanced composites. This summer, in July, AIM Photonics was announced. This is the American Institute for the Manufacturing of Integrated Photonics. And this you'll hear a lot more about from John Bowers. This is really about bringing the power of electronics together with the power of photonics or optics in a way in which we build an integrated platform so that we can use photonics in areas where it is best suited, and that's primarily around interconnection, and you'll hear more from John on that. And then just very recently, in August, another one of these institutes was actually announced by the, I think it was the Secretary of Defense in San Jose, and that is in the area of flexible hybrid electronics. And again, we from UCSB are participating in that. Michael Chabanek and Tim Chang are involved in those programs. There are a few more of these to come. It's already been indicated that one that's DoD sponsored in revolutionary fibers and textile manufacturing, and then one that, this is Department of Defense, Department of Energy led, will be in the area of a SPART Manufacturing Institute for Energy Efficiency, and Steve Denbars from UCSB is part of a team that is doing planning. When these programs come out, there's a call for proposals, so there are competitive proposals, consortia are put together, a proposal is made, and ultimately there's a judgment made and a winner declared. I guess you can ask the question, how have they decided which of these institutes should be formed? And that's been kind of a collaborative interaction between industry, government, and university. In the case of AIM Photonics that John will talk about, I actually had the good fortune of serving on a National Academy of Engineering committee that was set up about 4 years ago. I actually chaired the subcommittee on telecommunications. This was before the Obama initiative had been announced, and we were basically asked by the National Academy of Engineering and by the Department of Defense to address the question, where is optics and photonics going for the next 10 years? And what came out of that committee was a couple, and by the way, you should think about that whole issue of not outsourcing the manufacturing, so they were already thinking about it. So out of that white paper came a proposal that said what's going to be very important over the next 10 years is the application of optics within data centers. Data centers will be a huge part of our life, even though we don't see them most often. And optics, from a form of interconnect and increasingly actually improving the electronics that goes in, optics will play an important role. So in this particular case, I think it was just the new Obama centers coming out, manufacturing center coming out about the same time. There had been another proposal, and I would imagine that there are other kinds of situations where there's kind of been a growing interest in an area, and then now a recognition that with the help of these institutes, we will be able to turn these into technologies and products that can be manufactured in a cost-effective way in the US. So with that, I will stop, and now I'd like to introduce my colleague, John Bowers, who is, Umesh Mishra, who will speak to the power electronics. Umesh is a member of the Faculty of Electrical and Computer Engineering at UCSB, and he has been a pioneer in the whole area of high-speed electronics, and now in high-power, high-efficient electronics. Umesh.
Thank you, Rod. Thank you all for coming. I'm going to be talking about an institute called Power America. This institute is one that addresses what Rod talked about a little bit, is the whole concept of power conversion. Power conversion is a kind of a hidden thing. It's not very sexy. You can't see it. It's basically all the power that is wasted in converting power from the way it arrives, 110 volts AC at the outlet, and it's converted into the form we need, either 12 volts for your PC or to charge your iPhone or whatever else. So power arrives in a certain form and is consumed in a completely different form. And in that transformation process, there's loss. And that loss is huge. So 10% of all the electrical energy generated in the US is lost in this conversion process. That's $40 billion worth annually. So this is a hidden tax you pay on electricity. So even though it's not really visible, it's obvious to the touch. If you have an old school dimmer in your home, you touch it, you'll see it's warm. A mechanical switch is not warm. And the reason the old school dimmer is warm is because when it converts power from one form to the other, it generates heat. That's the loss. So the way you figure out loss is by touching something, not by seeing something. It's the heat. Anyway, Power America tries to address these issues. I'll rush through this. Thank you, Rod, for doing. So basically, there are lots of institutes, and more will pop up, and some with the Department of Defense and some with the Department of Energy. I'm part of the Power America Institute that's led by North Carolina State University in Raleigh, North Carolina. So basically, what does this national network do? What it does is it tries to basically do the following. It takes research universities, regional colleges, community colleges. Community colleges are a very big part of this. And NC State has made a huge effort in incorporating community colleges into this institute in Raleigh, and high schools. The federal government puts in a chunk of change, the industry matches it, and universities, after twisting Rod's arm, has also matched it. So thank you, Rod. Trade balance, we suck. Okay, that's the sign. And then the other thing is that this, of course, everybody agrees that even though we are recovering from the recession, it's been the slowest recovery. And one of the reasons is that many of the jobs lost are not being recovered. We have to create new kinds of jobs to recover from the recession. So it's not a V-shaped recovery. It's a kind of a very shallow U-shaped recovery. So what this does, let me tell you another thing which is kind of funky, okay? This is an institute which is housed in a university, but does not address, these are technology readiness levels, okay, TRLs. And universities typically hang around this area, basic principles, technology concept, blah, 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 right? And that's a really good thing. We do that well. This institute actually is beyond that. This institute targets system prototype demonstrations, models, breadboards, real things. And so what this institute is doing is pulling the university up the technology readiness level. And we're going there kicking and screaming because this is not something that we normally do. And we got to figure this out. It's okay. It's an experiment, as Leslie said. And we'll figure out how to do that. But what I'm saying is that this is not normal for a university to do. The nice thing about the University of California, Santa Barbara is we've had a history of entrepreneurship. So our faculty tend to look beyond the borders of academia. So we tend to kind of take to this, I mean, not quite like duck to water, but at least something to water, right? Michael Phelps to water. But we tend to actually go there more readily than many other universities, and that's why we've been so successful. This is the NC State has a lot of land compared to us, okay? So it goes off in plus and minus infinity in many directions, and so there are many centers they have there, and Power America sits here, and there are many. This is the Centennial campus, and this campus has a bunch of industries actually housed on campus, like ABB and other companies. So here's a general, this is from in the research triangle area. So if you basically go around and look for how many people, what is the qualification of hiring that people want, employers want? Oops, sorry, wrong button. 67 want an engineering or technology degree. This is actually real data from employers, okay? And business degrees, 36%, so on and so forth, law 11, and so on and so forth, and agriculture and biofuels about 4%. So this is what employers want. And within this domain, if you have an engineering technology degree, it basically doesn't mean you're just making things in hardware, software, marketing, sales, electrical engineers, so on and so forth. So there is no doubt that our country desperately needs engineers. That's what employers want. This is just a fact. We don't just produce enough of them. Now, let's talk about energy. And Leslie, you'll have to pull me, right? Because I have too many view graphs, right? So energy is a great problem. And it's a problem which is both a good thing and a bad thing, like everything in life, right? So China and India China emerging fast. I mean, India is about 25 years behind China in its economic growth. But, there's 1.2 billion here, about 1.1 billion here. You add Pakistan and Bangladesh, 1.5 billion. So between these two countries, you're about 2.5 billion people, right? And they're coming out of basically very low levels of middle class into a higher level of middle class. And what that means is there's a huge amount of energy that you need, and which is good. You don't want to, but it's you got to produce it. And in general, not only in India and China, our energy infrastructure is pretty old, and 50% of our power plants will be useless by 2040. We have to rebuild half our power plants. I mean, we tend to ignore repair, right? I mean, you drive on 101, you know that. So we tend to ignore the essential cost of repair, but the fact is 40% of the current fleet of plants have to be replaced. So now is an opportunity to figure out how much do you rebuild, how much do you save, and so on and so forth. If you look at the energy demand, it turns out that, of course, energy is the only thing that has a positive correlation with GDP. The richer the country, the more it consumes in energy. There's no other correlation, absolutely nothing else. It's one-to-one with energy. So what ends up happening is that the energy demand becomes actually economically difficult to match with generation. The demand for energy goes up like this. The way the supply can happen cannot match this. We can't build fast enough. So the best way of doing this is by consuming less while building more. And it's that combination which drives this particular institute. And by the way, we share a lot with John and Rod in the sense that what they are trying to do is also reduce consumption in things like data servers and everything. We are doing it for kind of old school, non-sexy stuff like motors and things that use oil and grease and stuff like that. So basically, you have a generating station, you have a lot of transmission lines, you have substations, you have a step-down transformer. So basically, you generate, you step up, you transmit at a very high voltage, you then bring it down. Then there are customers that use industries that use kilovolts, less kilovolts, and then us who use hundreds of volts. So there is a lot of conversion that's going on. And all of these conversions are lossy, and we have to make them all less lossy. That's the basic message I want to send. What you want to do is you want to have devices which are 1700 volts, semiconductors. Okay, to put this in perspective, the voltage in your microprocessor, the stuff that you use in your laptop, runs at sub 3 volts, right? 1.5 volts. I mean, that's what you go and buy at Ace, right? When you buy a battery, it's 1.5 volts. We're talking about the stuff that we are working on at UCSB is 1,700 volts. It's a semiconductor. And that's what we're trying to block, because these are the kinds of voltages we need to manage. Now, the beauty about it is, even though to make a smart grid, which we have to make, where we bring in, as Rod said, photovoltaics into the mix along with conventional devices, wind farms, photovoltaics, tidal energy, everything, as you bring it in, you have to actually be able to process bidirectional power control. That means you don't only take energy in and consume it, because sometimes you don't need the energy that is generated. For example, if when the sun is shining, the solar cell produces power whether you want it or not. So you have to be able to do many things. You have to be able to sell it back to the grid, and then have the grid ship it from, say, Arizona or California where the sun is shining to possibly Minnesota or Montana where it might be dark, or something like this, right? So we have to be able to either consume, we have to be able to take in and sell back. So this is a lot of control. There's a lot of electrical engineering, material science that goes on in this particular thing. And now I'm going to bring in a point which is called wide bandgap semiconductors. This is basically, wide bandgap semiconductors are semiconductors which are transparent, like gallium nitride. Wide bandgap means light can go through it, visible light can go through it. And that's basically a good way of looking at a wide bandgap semiconductor. That window pane is not a semiconductor, but it is wide bandgap because it's transparent. That's silicon dioxide. And so if you have a wide bandgap semiconductor, there's something very important about it, and this summarizes it. If you use silicon and you want to isolate 10,000 volts, 10 kilovolts, okay, which is not a lot of voltage in the scheme of things when you're transmitting voltage. I mean, for us, it's a whole lot, okay? You don't want anything close to this in your home. But in the grid, that's normal. If you want to actually hold off 10,000 volts, you need 1,000 microns of silicon, a millimeter of silicon. That's how much will hold 1,000 volts. Forget gallium arsenide, it's kind of an old school semiconductor. Let's look at gallium nitride and silicon carbide. These are the two wide bandgap semiconductors. Instead of 1,000 microns, you need 100. What? 5 minutes. Okay, so I'll move on after this very quickly. This point is very important. If you take a mechanical switch on the wall, the reason the switch is so efficient and cool is when you switch it on, two metals touch each other, and there is no resistance in the contact. And so it's a very low resistance contact, doesn't create any heat. In a semiconductor, when you turn this semiconductor on, you actually flood this semiconductor with current-carrying particles, electrons. But the distance cannot be changed. You can't just squish the semiconductor together to make a contact. So this thickness remains. So the thickness that holds the voltage is also contributing to resistance when you turn the device on. So the thinner the material to hold the voltage, the less resistance when you turn it on. 10 times less resistance. Big deal. And this is why, because what happens is that resistance is loss, okay? And if you have 10 times less resistance, 10 times less loss, it's a big deal. So I'm going to move on to so the goal is, at the end of the day, what this institute does is it wants us to keep working, and in a decade, make these new semiconductors. By the way, this semiconductor is not very new. It's the same thing that Nakamura got the Nobel Prize for. It's the same thing that puts out blue light, okay? We are just using it for another purpose. So Power America allows us to make this get better and cheaper so that the bullseye is to be as inexpensive as the competing technology, which is silicon. Okay, so this is silicon carbide. It's a 6-inch wafer of silicon carbide. It's being processed in a silicon foundry. This silicon foundry is X-Fab in Texas. It's an old foundry that basically has got a new lease of life. It would never have survived running silicon. It's now running silicon carbide, for example. On gallium nitride, unfortunately or fortunately, we are the only game in town. Transform is the company we started out of UCSB. And here there's a wafer fab and factory here. We also have a partnership with Fujitsu, and we basically do manufacturing both here and in Japan. So this is not quite very much in line with the institute in the sense that why are you doing anything in Japan? Because At the end of the day, what you have to do is you have to do what you have to do, and once you succeed, typically what ends up happening is, this is what American companies do very well. Once you succeed, if you really succeed, they buy you and do whatever is the right thing to do. So right now we're doing it in both places, and we'll see what happens. That's basically. UCSB has been working on this. This didn't come about by accident, just like John has been doing this stuff forever. He's a young man, so not ever, but fairly ever. And we have been doing gallium nitride for a very long time, since 1994. We actually jumped on this bandwagon the minute we saw Nakamura's blue LED. I remember Steve Denberg calling me to his office and showing me a Japanese publication. I said, what the hell is this? And he said, it's a blue light. I said, so? And he says, this thing works. I said, what is it? He said, gallium nitride. I said, are you in? He said, yeah, I'm in. So I said, I'm in. And we just shut down everything we were doing and moved into this technology. Huge risk, but turned out to be very rewarding. 1994 is when we started. We've gone through one successful spin-off, Nitrous, which was acquired by Cree in 2000, and now we've transformed. The good thing is, the stuff we are making is being sold. Okay, that's important. So it's being sold in India. India is now going through a massive solar expansion. They're going to put in over $100 billion in solar investment. And because that's the quickest way in which they can generate energy and still meet climate change issues. And the one last thing I'd like to leave you with is, education is a big part of this institute. So in 2001, we have 4.01 million ninth graders, and then there were dropouts, 2.8 million high school grads, dropouts, 1.9 million college people with plans to go to college, only 1.3 million were college ready, and then out of the 1.3 million, 278 were majoring in STEM, and at the end of the day, we had 167,000 STEM graduates. This is fundamentally one of the big parts of the Institute I don't want you to forget. We are trying to kind of plug these leaks, okay? That's also one of the big part of the Institute. With that, I thank you very much. And let me introduce, well, he needs no introduction, but John is going to speak about the main event, which is the Institute AIM.
Thank you, Umesh. Thank you all for coming. We'd like to talk about the photonics end of this. I'd like to start off and initially just talk about why photonics matters to you and sort of what we're all going through as a society, and the transformation which is driving photonics. And so, as it says here, it's a big investment. It's $110 million. It's the largest IMI of all of them. And it's got a total of about $600 million worth of matching, so pretty significant commitments. The amount in Santa Barbara area is smaller, but still significant, probably about 15 million federal over 5 years, and 8 million state and 10 million industrial. And again, most of the state money is workforce development, and we have good collaboration with Santa Barbara City College in particular, and other city colleges around the state. So there's a lot of faculty involved at UCSB is listed here. It's not just me, it's like at least 10 of us. And then a lot of industry overall, but certainly these are the industries on the West Coast that we're involved in. So, in terms of why photonics matters, so we're all used to this transformation from broadcast television to cable television, and we all have lots of DVRs, and so we store all these TV shows that we don't want to watch the commercials on. But that's really stupid, right? I mean, why have 100 million DVRs and 100 million hard drives inside those DVRs? Why not just have a couple data centers, store orange is the new black once, and then just distribute it. When you want to watch it, send it. If you want to watch it, send it 2 seconds later. It's really a waste to build all these DVRs. It's really stupid. Same thing, in general, Netflix now accounts for 30% of internet traffic in the evening. So it's everyone downloading television shows, downloading movies, downloading music, downloading newspapers. And in general, it's just much more efficient to store all this in a central location, maybe a few of them around the country, and distribute it. It's from a societal point of view, data centers are really a much more efficient way for us to live, and a lot of things are obviously changing as a result. So you get this very explosive growth in data centers. And again, all of you know this. This is just some data if you want to see it. But it's about 35% compound growth for cloud data centers. And that means, just 3 years, you've got to double the amount of data centers you have. So the amount of money going into building data centers is huge. So maybe you don't need so many DVRs anymore, but you need a lot more data center investment. And fundamentally, that's what I'll talk about today. So it says here a total of 7.7 zettabytes is now what we're going to be at by 2017. In case you're not up on your acronyms, goes kilo, mega, giga, tera, peta, exa, and zeta. So 7 zettabytes is 10 to the 21 bytes, or about 10 to the 22 bits. That's a lot of data that's being stored. So here's a data center. This is a Google data center. I think this one's in Oregon. It's big, right? It's like a football field sort of size. And if you look around the outside of this, these are all the cooling towers that expel all the energy inside, right? So a big data center has, say, 1 million servers inside of it. And you take 1 million servers, each running watts of power. You've got to expel all of that energy. And so if you can make more efficient everything, more efficient power supplies, as Umesh talked about, more efficient servers. I don't know if we can lower the gain here a little. All right, I'll get closer. Thank you. I'll keep my, okay. More efficient servers, power supplies, and data transmission between those. That's the goal. So here's again a data center, Google data center. There's lots of pipes to get all of that energy out of that data center. And anything we do to make it more efficient is important. And so photonics will displace electronics for switching or interconnects, provided it's cheaper and provided it takes less power. So again, a data center over its lifetime costs as much in power as it does for everything inside of it. So the cost of the servers and the routers and everything is the same as the amount of cost dollars it takes to generate that signal. So again, here's the second to last photograph of data centers, lots and lots of racks. And then within that rack, lots of servers. Each of those boards probably has 20 servers on it. And the top of it is a top of rack switch that communicates with other racks around that data center. So again, you take all those racks and connect them together, and those racks are all interconnected with optical fibers. And so that's where fiber has penetrated. And so a data center like this will have something like tens of thousands of fibers. So why are there optical fibers in a data center? So the fundamental reason is about fourfold. So this is a coax cable, like you'd have coming from Cox Cable in your house. And that's an optical fiber. So it's a lot smaller, it's a lot more flexible, and it's actually a lot cheaper today. So for even just connectors like to drive this display from that computer, say, are cheaper today optically than they are electrically. So that's part of it. And part of it is that fiber has 10,000 times less loss. So again, it used to be Cox Cable would run cables down Cathedral Oaks or down Hollister and distribute their cable systems. If you now replace those optical fibers, you can go a lot further before you need to re-amplify that signal. So again, it's a lot more efficient. The third point is that it has a lot more capacity, about 10,000 times more capacity. So what's plotted here is capacity versus time, and we're now up to something like 100 terabits per second can go down a single optical fiber. The little thin thing I showed before can carry 100 terabits of data. So that's the big advantage. And so it's smaller, lighter, cheaper, more flexible, much less loss, much higher capacity. That's why people use fibers. And then finally is, in the end, these links typically take about 10 times less power. And the higher data rate you go, the less power, the more efficient they are, because it takes a lot of equalization to send 50, 100 gigabit data down an electrical wire. It's much better to do it optically. So that's the motivation for why fiber matters. So today, that top of rack switch I showed is connected to all the other rack switches optically. That part is fiber. But within that rack, everything is electrically connected. It's just the same sort of Ethernet cable you might have in your house, for example. And so the big push now is within that rack, all these companies, Intel, Orion, HP in particular, want to replace that with fiber optics instead of electrical wires. And that is happening. It hasn't happened yet to any significant extent. It has happened within supercomputers. So this is an IBM 775 supercomputer. Here's the back of the rack. So now within that rack, there's optical fibers. That's what all these orange cables are. And if you look behind a whole bunch of these that are all interconnected together, it's a huge mess. So that is not very high capacity optical fiber, but that's an example of replacing electrical cables with optical fiber. And so it wouldn't have been possible to do that electrically. You can at least do it optically, but it isn't very, very good. So as it says here, we need as much more higher bandwidth per fiber. So that each of those fibers is probably carrying about a gigabit of data. We need to get it to be at least a terabit, if not 100 terabits. And so there's a lot of things to do. Wavelength division multiplexing, multi-core fibers, and higher data rates are all the trends of what's going on. Here's another picture. This is, again, another supercomputer, the IBM Sequoia. And this Blue Gene computer has about 1 million optical links inside of it. So, you know, that's a big transformation. 10 years ago, there were very few optical fibers in there. But now it's a significant number. So going back to data centers, and I want to now connect with a couple local companies. This is the architecture one of the architectures that's commonly used. This is what Microsoft has. So you've got a bunch of racks. Each of these vertical lines here is a rack. So again, it has, 1,000 servers in it, something like that. They're connected to this top of rack switch, and that top of rack switch is connected through other switches, leaf switches, that are connected to other switches, spine switches, and then that's connected to the outside world. So when you send your request for, what day is Thanksgiving next year, then that comes in here, and it may be just a few bits of data, but it gets distributed to some number of servers down here that figure out the answer to your question. So most of the data is being transmitted inside the data center. Only relatively little amount gets out. So you may make a simple request, but it ends up having a lot of servers involved in answering that question that you may ask it. So two companies involved in this area is Caliant. I'll show a slide on that. And they make switches. And in particular, what they make is a very high radix switch. Radix is just the number of ports on that switch. And again, if you think about a data center with 1 million servers inside of it, you want as many ports as possible to connect up to other switches rather than you want as large a switch as possible. So this is what Caliant makes, and Greg Koss is here somewhere from Caliant. But this is the 320 port switch which is made, and that's a great success story for fiber optics, optical components being made in Goleta. And so it is cost effective to make it here. And this model is very much like what AIM is about, because the silicon core optical switching elements are all made in a silicon foundry, and then those all come back here and they get packaged up, and the rest of this gets assembled and shipped from here.
A second example is shown here. This is a silicon photonic integrated circuit made by Orion, and it is an example of a 100 gigabit interface, which is where the field is going next, and it shows integration of different components on silicon. Again, because silicon is a very poor light emitter, putting 3 5s on silicon is what makes this work. And they show the schematic in the center, and in the lower right you can see a packaged 100 gigabit prototype. And again, that's a classic example of the design team is in Goleta, and the fabrication is done in silicon foundries elsewhere in the United States. So the next slide shows the general trend of where we believe the field is going. This is a slide from Intel, and they have a big heterogeneous silicon effort, as I've been talking about, made in CMOS foundries. And what it shows here is on the left, the existing optical networks are all fiber optic, and that's on long haul scale and a metro scale, and as it shows here, on the level of rack to rack in the center. And the goal of this is to move this transition from where do you have optical to where you have copper down to basically chip to chip. And the advantage in this is the volumes are billions rather than thousands, and the costs have to be much lower per chip, such that we can all afford it. So the next slide shows where we're generally headed, which is rather than today where we have silicon chips in little packages that are cages basically, CFP packages, moving increasingly down to where the fibers go across circuit boards and go directly onto the chips themselves. This is a huge increase in efficiency because you don't need to do all the equalization and SerDes, serial deserial recovery of the signals, and consequently it takes much less power. And that's what's important in the data center. So the slide here is why silicon? If you want to do photonics, that's fine, but why do it on silicon? Especially because silicon is such a poor light emitter. And the reason is we want to make it in a silicon foundry, in a CMOS foundry, large wafers. We want to do 3D stacking, as shown in the lower right here, of optical wafers on electronic wafers. And just as shown here, combining typically many layers of electronic chips, perhaps memory on top of processors on top of a photonic layer shown in the bottom here. And the fact that we've leveraged this CMOS facility that's doing high volume electronics means it can be very inexpensive. And we want to ride this revolution basically in 3D stacking of silicon chips and add one more, which is the photonic layer. The next slide here shows the evolution of silicon photonics. It was first proposed in 1987 by Richard Soreff, and for the first 15 years very little happened. But about 2005 the field took off, and it's now lots of groups around the world are working in this field, and we have something like 2,500 papers per year published on silicon photonics, all kinds of aspects of it, from lasers to modulators to detectors to passive components. This slide shows all the companies working in silicon photonics. On the left are largely brand new companies, startups that are working in silicon photonics. Luxtera is in Southern California, Orion's in Goleta, Scorpios is in New Mexico. The companies in the center are utilizing silicon photonics, Intel for data centers, IBM for supercomputers, HP for supercomputers, Cisco for routers, Photonics for switches. On the right-hand side are foundries that companies can use to fabricate these chips. So Orion and others can submit designs that get fabricated at these foundries that are located around the globe. The next slide shows the way that we get lasers on silicon. So the hard part is that silicon is indirect band gap. It's a very inefficient light emitter. But by putting a thin film of 3,5 materials like indium phosphide or gallium arsenide or gallium nitride on silicon, we can get light emission at the wavelengths that we need. And so that's shown here on the left. We put down these wafers of 3,5 material and etch off the substrate, and then we fabricate lasers, as shown on the right. And on the bottom, you can see the guy that did this for his PhD thesis, Alex Fung, who's the CEO of Orion. And then you can see some blow-ups of what these structures actually look like. So that's the way that we can get lasers and a complete photonic integrated circuit on silicon. The next slide summarizes this new institute, the American Institute for Manufacturing Integrated Photonics, that has been set up by the Obama administration, and it's $110 million of funding, matched with about $500 million of state and industrial funding. And the goal here is to make, in particular, silicon photonics, but all photonics, in the United States. And so develop that manufacturing technology so that it's a strong industry and can lead towards fiber to the home, data centers, supercomputers, and elsewhere. The next slide shows the different industries involved. So again, we have tier one industries that are committing $1 million per year to this project. So again, Intel, IBM, Infinera is an indium phosphide company, HP, and then a lot of the design companies like Cadence, Mentor Graphics, and Synopsys. Tier two are companies that are lower level of commitment, but again, companies like Lockheed Martin that want to use this in defense, or TE and cables. And then on the right, you can see the universities that are involved. So the three main universities are SUNY, UCSB, and MIT, and then Rochester Institute of Technology, University of Rochester, Davis, Arizona, and Columbia are major players as well. The next slide shows why we use SUNY as the manufacturing hub for this institute. And you can see here there are 5 buildings dedicated towards building integrated circuits. And one of these in particular, NanoFab North, is the one that we'll be using for photonics. But it's a 1.3 million square foot facility with an amazing 135,000 square feet of class 1 clean room, which is a phenomenal capability. And you can make devices from 65 nanometer, which is where we'll be focused for photonics, all the way down to 7 nanometer for the most advanced electronics. This slide shows one example of the projects we're working on. So this shows, again, a high radix switch. We talked about them before for Caliant. This is one that can switch faster. Its size is smaller because the architecture is different. But this is a very complicated photonic integrated circuit. There'll probably be over 1,000 elements integrated together. So it's likely to be the most complicated photonic integrated circuit that's been made to date. And it would sit in the center of a data center and connect together lots of other top-of-rack switches or spline switches connected to different server configurations. This next slide shows the 4 initial projects we're going to be pursuing. On the upper left is the high radix switch I just mentioned. On the right is applying photonics to make more efficient and less expensive microwave cables. And so for applications like, airplanes and ships and things, a large amount of weight and cost goes into interconnecting antennas with control centers. We can do that optically very efficiently. The bottom left is applying photonics to make photonic sensors for chem bio, so detecting, things like, nitroglycerin or explosives or chemical agents. And we're doing this by combining a photonic spectrometer together with a microfluidic sensor for gas or liquids. And the bottom right is the last example of pursuing a phased array technology that could be used for free space optical communications, for example. This next slide is one of the ways we're looking to put 3.5s in silicon. I talked about bonding before. This is growing it epitaxially. And the key thing that needs to be done there is to now epitaxially grow quantum dots rather than quantum wells. And the goal here is to make devices that survive the large lattice mismatch that occurs between 3.5 and silicon. And as you can see here, we've demonstrated quite good devices. These are 180 milliwatts CW. It's a huge amount of power. And we want to do this in a manufacturable way that we can transfer to SUNY and integrate with the rest of photonics. So this slide here, Moore's Law for Photonics, summarizes the field. The blue are all the photonic integrated circuits that have been made to date on indium phosphide, which has been the most advanced platform so far. And upwards of, hundreds of devices integrated together. So far less than electronics, where you get, 7 billion transistors on a chip. But this is a fairly complex photonic integrated circuit. The red shows the silicon photonic chips that have been made to date, several thousand devices integrated together, but without lasers. The green triangles show the components that have been integrated with lasers on it, this heterogeneous integration process I've just been talking about. And we're up to a few hundred now, and under AIM, we plan to go to thousands and perhaps even 1 million devices integrated together. So to summarize, silicon photonic integrated circuits are here. They're being pursued by a number of companies like Intel, HP, Orion. It's a major focus of AIM, and our goal here is to improve all the manufacturing aspects of it. So higher yields, lower cost, better reliability. And the message for everyone here is that AIM is looking for industrial partners. So the whole goal is to transition this technology to enable new fields and new products for large companies and small companies. And we're looking to partner with companies across the United States. So what's listed here are a couple of web addresses. You can check out more information on AIM or on the optoelectronics research going on at UCSB. Thank you.
they evolve. I mean, there's an idea, there's a thought process that it'll work, and then you start working on it, and then you got to tweak it because it really doesn't quite work the way you planned it to work. So at the moment, the way it is first of all, when the first, at least in the institute I'm involved with, the first big hurdle that came about was a lot of doing things in America is absolutely the goal, but if you look at our member companies, they're international companies, right? So you end up in this situation as trying to figure out what is really American, right? So you have to then redefine, okay, if the company has an office or does some work in America, it's American, and that's fair. And that was the first hurdle. That was the Americanness hurdle, which was actually a tough one, but we've gone past that. And now it's trying to make sure that the university actually does what I talked about, this TRL4, this Technology Readiness Level 4. One of the things we have to do is make sure that this also ends up educating students, because at the end of the day, we are an educational institution and people have to get a PhD. So there has to be enough science and technology to justify a PhD while paying homage to the idea of the institute. So that is another aspect, and that has been worked out too. So once it's all the issue of labels. Once you have a label, you have to make sure what does that label actually define, and then you have to work the label a little bit to make sure that people fit. So the biggest problem we've had up till now is just the mechanics of actually fitting into labels. And then I think the best thing, and the old adage always works, that is, if people start doing things and they start working, then people adjust the label a little bit, because people always like winners. So what has happened is, it's a little bit of, let's start doing something, independent of whether it's really exactly correct. And if it turns out to be right, then let's see if we can expand the tent to fit it inside. So it's taken a year, and it's been difficult. To just get this whole thing going, but it's kind of now working by everybody adjusting things a little bit, and it's been working okay now, but it's taken a whole year. So that's what you have to look forward to, John.
Well, I think for us, and I think all the institutes, the metric is industry engagement, right? So there are metrics like how many companies are involved, and particularly how many small companies are involved. So again, if there's any existing startups or new startups that get engaged and end up making things through these multi-project wafers that will get made, then that's success. That's what we get graded by. So it's not how many universities are involved or how many grad students get turned out. It's how many companies get involved and how many jobs are created. So we haven't yet had to satisfy that metric, but before 5 years is over, guaranteed we'll have to say, how many jobs did you create with this institute? And if that number isn't a significant number, then we failed. So anyone here? I see Bill Parrish back there. So great example of an entrepreneur, and the government is pushing for a particular camera, by the way, Bill. It instantaneously generates 10 terabits of data, and they would like to put an optical interface on that to get the 10 terabits of data off that camera. So that's a project we'll probably look at.
So maybe I can just add, because in terms of the model, fundamentally, a couple of things are happening in this program. One is, fundamentally, we are trying to bridge from a technology to a product, but we're not doing that for a single product. We're doing that for a whole industry. And so the model, in order to do that, is to do better than what one company alone could do if they were going after this, particularly given the investment, not just in the research and development, but in the tooling and the manufacturing infrastructure. That's one of the reasons you hear about silicon photonics. It's leveraging the existing silicon technology and applying it and adding to it the optics that is so necessary, as John has pointed out, to overcome the interconnect problem, right? The low loss, low power interconnection, which started connecting around the world, reached out and became the key technology for metro, increasingly as the technology out to your home. That's fiber optics, and now it's found its way into data centers. And as you see, increasingly, as you go to higher and higher rates, the value proposition for optics as the way of interconnecting is cost effective, even down to very, very short distances. And that can make many things happen. One company doing it on their own, particularly given the infrastructure, the ecosystem around it that's necessary. In electronics, there's a whole industry around electronic design, which allows people who know nothing about silicon processing to design circuits that can have huge functionality. We have none of that in photonics. So that has to be built. Now, how do you do that? How do you bring companies together that might be competitors? Because we've got them. We've got Intel, we've got HP, they're competitors. But they've agreed that in order to build the ecosystem, to make this happen in a way that it's cost effective, whether this is about jobs in the US or not, from their point of view, probably not the issue. They want to develop this industry in a way in which they can leverage it. We're hoping we can do it in a way in which we keep the jobs here. But by these institutes, we build infrastructure. We bring companies together who agree to work together because they believe by working together, they can then take what they learn out of that, run as fast as they can to then compete with the same people they were partnering with in the past, or to segment the industry so that they're partnering with the electronic design people. That's not their business. They want to make sure that that gets developed. So that's part of the difficulty that Umesh talks about in terms of getting these things going, because in the end, it really requires that the companies trust each other and trust the universities, people they don't always work with so much, and trust government, which is an important part of this. And the government's an important part of it because they're putting lots of money into it. And where's that money coming from? Well, Obama announced the initiative, but can you imagine getting this initiative through the Congress? Absolutely not. So the money is actually coming from the federal agencies, Department of Energy and Department of Defense, and they're willing to put the money in because they believe if they put it into this single platform, they'll end up getting more out of that than if they fund a whole bunch of smaller projects in different platforms. So there's the potential for a win-win for every side of this three-way partnership. But you know how these things work. It takes getting acquainted, getting a level of trust, getting a level of respect for what the other entity does. And so that's kind of the process that we all have to go through. We're hoping it won't take a year for AIM.
Now, if I can just add one small thing, because I wanted to follow up on what Rod said. He talked about this ability for people to design into a silicon foundry. In fact, one of the goals of our institute is to actually create also a foundry. It has happened in silicon carbide. It's being developed in gallium nitride so that people can actually design into that foundry in this new material system. Just like photonics doesn't have one, wide bandgap power semiconductors doesn't have one either. So that is another thing where we actually have the same desire. Also, what John mentioned was, he can actually go into an existing foundry, a 12-inch foundry, in which they can do their photonics. We have a kind of a collateral kind of benefit, not the 12-inch foundry, but there are many foundries shutting down, and they happen to be in states like Pennsylvania, Vermont, other places where legacy foundries are being shut down because they're not cost competitive. In these legacy foundries, which are the 6-inch foundries, which John said are no longer competitive, we can actually run these new semiconductors, which are not 12-inch wafers, but 6-inch wafers. So you can actually use existing fully depreciated fabs where you're only paying operating cost and no depreciation to develop a whole new technology. This is also something that the government is very interested in.
So essentially creating platforms that things can be built on, and also leveraging off facilities that are already in existence. So that is pretty incredible. So I think we should start with our Q&A with our audience, and we'll start with you.
Hi, thanks for the wonderful talk. I'm a little bit curious about the university's position on sort of getting these innovations out, you know, as you're talking about, to companies and industry. When you think about what strategic partners are looking for, it's sometimes something that's far enough along to take it and commercialize it. So that's this technology readiness level 4. But also when you think about job drivers and having small companies take these technologies on and really develop them and commercialize them, that may be a great opportunity for job creation. So I'm curious, is the university looking to do partnerships with smaller companies and spin-offs, or are they really looking to just get this out to big industry that can immediately commercialize?
I think the biggest focus is small and medium-sized businesses. So that's been the charter from Obama. You know, the belief, which I think is true, that most jobs are created in small businesses. So that's the highest criteria for us. And again, the goal is this photonic design kit doesn't exist today, but within a year, it should be pretty good. That's the intent. And we'll keep evolving over time. So any circuit designers out there that are familiar with, you know, Cadence or Mentor, the intent is you can sit down and design your photonic integrated circuit in Cadence, and you'll know exactly how it should perform, and it'll be fabricated with the cadence of this year 2 multi-project runs, next year 3, the year after that 4. So every quarter there'll be a new design coming out that anyone can tap into. So there's a price per square millimeter, just like there would be with Moses, and anyone can have a pick made. So to me, that's a huge advance. Any of the companies out here today that want to do photonics, you know, you're limited to what can you buy. I can buy a laser from this company, a detector from this company, but now you can actually do whatever integration you want to do a year from now. So
it really substantially reduces the barrier to entry for small companies to leverage this technology. And the fact that an Intel or an HP says that's okay is because they believe that out of this, they will learn from the participation of those members as well.
Interesting. How do you handle the IP? Because I'm sure you have competing companies, you have universities who want to own it, you don't want to disseminate it to people who don't belong. What do you do?
So there is an IP policy, and so we will, like for instance at UCSB, be generating IP that becomes owned by the AIM Institute. And so any of the companies that have signed up, I'm not sure about the details between Tier 1, Tier 2, will probably have a royalty-free license to that, non-exclusive license. So the main thing is develop technologies that the foundry can then disseminate to other companies, you know, to use for fabrication. So again, SUNY's capacity is at least, they would state at least 10,000 wafers per year. So their goal is to do reasonable sized manufacturing for companies, and they do it today. So again, Semitech was there, and they did a lot of work for Semitech for a lot of years.
I have a question. So I'm sorely ignorant in photonics, but what I'm hearing and I'm a little concerned about is that Obama is sending all this money to the universities and to industry, and yet the jobs get shipped to overseas. So you've got the $100 billion solar project in India, and what are we doing to keep the jobs here?
So the interesting thing about the India event is kind of so let me see how the $100 billion are spent in India. Most of the $100 billion in India are not spent on anything made in India. In fact, the biggest problem in India, the new Prime Minister is trying to do a Make in India push. just like Obama is trying to do a make in the USA push. So selling into the US so everything that goes into, right now, that is going into the India PV inverter market, which is going to open up in April with our devices, the material is all grown in Goleta. So basically, the material is grown here, it's fabricated partly here and partly in Japan, as I had mentioned. And then, but the technology and the jobs are created here. We just sell it into India. So it's actually a good thing. And in fact, we are getting the US Trade Development Agency putting in money to help this whole process, because what it does is it creates American jobs and sales in India. Now, if India starts making it, that's a whole different matter, but that'll be something in the future, not. So that's, what you're concerned about is right. I mean, if you spend all this money, will you create jobs here? And there is no one-to-one correlation, correct me if I'm wrong. I mean, it'll kind of, you will create more jobs, but most of the jobs are going to be created in small businesses that don't exist today. You'll find a lot of new businesses, just like Transform didn't exist 5 years ago. And I'm a big believer in small business creation, the ease, the lower barrier to entry that Rod talked about. God knows how many new businesses are going to start. So I believe that it's not Intel that's going to create a whole lot of new jobs. I think they will, but most of it will be jobs from people who are just innovating.
So in the case of photonics, again, it's all about manufacture, but it's manufacturing that includes packaging. If you look at the optics and photonics industry today, the core elements that go into that are often made in the US. The packaging, where you put the pieces together, including this fiber, right, that you have to carefully attach to the end of the chip because light's coming out or light's going in, that's labor intensive. And that traditionally now is being done someplace. The fact that we will do this on a silicon platform and will be done, and the goal is then to design it in a way in which you're designing the package solution at the same time, automated, self-aligned, with very little human intervention. Now, you can argue that in some cases the jobs are going to go to robots, right? I mean, so that's a valid thing. But then you build a whole ecosystem around that industry and keep the leading edge of that, right? Basically, the intellectual property and the advanced development in the U.S. But will there be jobs going out? Yes. But the intent here is to keep as much of the value. At least that's the Obama intention, and the intention of how these get organized is that the net result is that you keep the largest part of the value here in the U.S.
If I could just go back to Bill's question, because I didn't answer it very well, I realize. So my answer is correct. If you're receiving money either at a company or at a university from the federal government, that IP is owned by the institute. But if you as a company come in and want to have something built, then you own that IP. And you can either share in a multi-project wafer run, and there are proprietary agreements. No one else should ever see what you put on that mask. Or you can buy a complete wafer set yourself and have that fabricated. So there's lots of one-to-one relationships with particular companies where no one else even knows they're a member.
And I guess I would just add one thing to the ownership of the patents. The patents will still be owned by the university if we are the inventors, because but there will be a license-free, a royalty-free license that goes to members of the institute.
But if you fund your research, then you own your IP. The institute has nothing to do with it.
And there's actually in the AIM program. So we actually call them Type A and Type B projects. And Type B projects are literally where the facilities of the fab are used, but the projects are totally owned by the company. Quite frankly, that's an important part of the sustainability of this, the cost sustainability of this as well, because we know there will be partners who want to keep that intellectual property and are willing then to pay the full load of actually developing it through the platform.
So I think we have time for one more question, so we'll take it from the
So
back.
I have a very fundamental question. So thank you for your presentation, and very well done, and congratulations. And I absolutely believe this is the future. But the one thing that's lost on me is not job creation, but the fundamental fact that we have an ailing infrastructure throughout the United States. So how does this solve our infrastructure problem? Because it's been forecasted that here in Santa Barbara, if we have a bad El Nino, our entire grid could go down, right? So for me, having worked in management consulting way back when, there's a fundamental business problem or a fundamental need that's not being met in this. And I agree, this is a future, this is great. There's a lot of opportunity. I'm sure you'll create a lot of jobs, but does it solve the problem? And the problem is near term. So how will this be able to be rolled out, and how will it evolve over time so we can solve the big problem, which is infrastructure that's falling apart?
And the infrastructure you're talking about is roads and trains and...
No, I'm talking about
the
the
grid?
grid, our
The power grid.
throughout
Okay.
America. It's all based on dated technology that's literally falling over. And, you know, there's an organization here, I don't know if you work with them at all, the World Business Academy, but that's their whole deal. Like, they're trying to finance using solar, photovoltaics to replace our local grid, because they say that we literally could lose power throughout, the Central Coast because it's degrading so badly. So anyway, I think this is fabulous, and what you're doing is amazing and wonderful, and I'm sure that it's the future. But how do we get from now to there, knowing that everything else is failing?
So I'll just put my own kind of quick view on it. For me, I would turn that around and say the good news is that while the grid is falling apart, the value proposition of upgrading it is now there, so it's not just rebuilding the same thing over again, right? So that doesn't solve the very short-term problem of a disaster, but at least gives financial justification for rebuilding that grid in a way that's modern, takes advantage of photovoltaics, takes advantage of more energy-efficient technologies. So that will help make it happen in a way that would otherwise be very difficult, I think.
So Pedro Pizarro, the president of Southern California Edison, spoke here, about 2 weeks ago at UCSB campus. And he mentioned that there will be a major microgrid project probably in Santa Barbara. So they are going to roll out some major, it's a lot of money, it's a lot of storage. So again, we're at the end of the line, Southern California's line, and that's perhaps one of the reasons that microgrid project will probably be done here first.
And if you look at, you take, say, your point is very well taken, and Rod also addressed this. Just rebuilding more of the same is probably not a very good idea at all, and this gives us an opportunity to actually bring in much more distributed generation of all kinds. And in fact, if you go on the DOE website, and so that I'm not smoking crack. I mean, this is basically it's actually software developed by ABB, and they've run it that by 2035, if you're committed to it, 98% of the US energy can be renewable. Combination of all kinds of things, for example, wind in the right place, tidal in the right place, solar in the right place, and so on and so forth. And it's so it's not insane to think that we can actually go down that path of going for more distributed generation. And so I totally believe it's an opportunity. Just building more of the same, I think, is a bad idea.
I don't know if anybody's read the National Geographic from last month, but they did talk about Germany's approach to going 50% renewable by 2025, and that they actually are in advance of that goal, and that they really do believe that rather than have a centralized grid, that their approach is, these nodes. Is very interesting. I mean, their only challenge is coal, because they can't, that's kind of the essence of their current economy in terms of energy.
Well, they have problems with sunlight, too.
Yeah, well,
So,
but
I mean,
they,
that makes their goal even more bold, is really the point, right?
Right.
'Cause
they've done some very creative things. But on that note, I think since it is probably exactly 7:30 and I try to always be on time, this would be a really good time to thank the audience. So I thank you very much. And then I very much want to thank the speakers, and if you have questions at this point, I think it's a good time to just get up, talk to each other, and enjoy the rest of the evening. Thank you.
Thank you.